Welcome to IMSE881 Linear Programming class. Today we're going to talk about Lecture 12 and the algorithm with this interior point algorithm we're going to discuss is the Primal-Dual Affine scaling algorithm, and it's also referring as the path following algorithm. First, introduce the primal and the dual linear programming model. First, we call it P1, is minimize the C transpose times X with the standard form of the constraint of subject to AX equal to B, and X is non-negative. Also, its corresponding dual problem called a D1 is a maximization of B transpose times omega and subject to A transpose times omega plus S. S is the dual slack equal to C. And for here, S is non-negative and the omega is unrestricted since the primal constraints are equality constraint. Okay, since the primal variable also is greater than equals to non-negative, so therefore the dual constraint should be less than equal to constraint. That's why we're adding a dual slack right here to make a standard form. Several assumptions to go over. Okay, the set of S, which is the feasible region for primal problem, is a set of X belongs to n-dimensional Euclidean space and satisfy AX equal to B, and X is strictly positive. So, and we said the S is non-empty set, which is the relative interior for the primal feasible region. Similarly, the T is the relative interior for the dual formulation. The set of vector omega and S belongs to m-dimensional Euclidean space times n-dimensional Euclidean space because S is n-dimensional. And satisfying the constraint of A transpose times omega plus S equal to C, and S slack variable is non-negative, and the dual variable is unrestricted. And we assume this T set of point of T is non-empty as well. Another basic assumption is A has a full row rank, and meaning the dimension, the rank of the A is M. M is less than N in that sense. Okay, so S and NTs are the relative interior. P is, we have three possible, okay, and P1 has a bounded optimal solution, and D1 has a bounded also optimal solution as well, omega star and S star. And also at the optimal, C transpose times X star equals to B transpose times omega star. So this is a basic assumption. For now, we say there's a bounded optimal solution for both primal and dual problem formulation. And at the optimal, the primal objective function value equals to the dual objective function value. Next, let's review some duality theory related information. In order to keep the current primal solution xk within the relative interior of S in the S, and dual solution omega k and sk within T at each iteration, we're going to use some logarithm barrier function technique to prevent the X and S, basically, the xk and sk are strictly positive. So what we do is first we're going to define a problem P mu based on the minimization of C transpose times X minus the mu times the summation of natural log of xj. Let's take a look at the natural log of xj function. Of course, the constraints stay the same. Ax equal to b, x is non-negative. So where it mu is a barrier and penalty term we use. Look at this graph. So if x is closer to 0 and the penalty increase to almost infinity, and this is exemplary. So since the negative in front of here represent, and therefore this will be against the minimization problem, because this term itself is a negative, plus the negative becomes a very huge positive, and that's the -3 right here represents. So we're trying to prevent or create a barrier function, preventing x is getting too close to 0 in that case. And as algorithm progressing, we gradually reduce mu becomes to 0. Then the optimal solution of the p mu will be converged to optimal solution of p1. So this is the idea. So systematically, we're going to reduce mu from a positive number all the way to 0, or very close to 0. Okay, since the objective function of p mu now is nonlinear instead of linear with the logarithm barrier function involved. However, it is still strictly convex problem. It's strictly convex for the negative natural log, and plus a linear term c transpose times x, and therefore this is still strictly convex. And based on the theory, the unique optimal solution still exists. So this is the idea how to using a log barrier function to prevent the current primal solutions getting too close to 0. And the KKT condition for p mu is still three part. We talked about this before. It should be the primal feasibility and the dual feasibility and the complementary slackness condition. So here we have the capital X represent the diagonal of current X solution. Capital S represent the matrix capital S represent a matrix with diagonal equal to current dual slack. Then of course E is a vector of 1 with a dimension of n in that case. Same thing for the log barrier function for the dual. We define a dual mu based on the maximization of b transpose times omega plus mu times the summation of the natural log of s. And this is another similar barrier function trying to prevent the dual slack sj going too close to 0 as well. And we subject to the dual constraint a transpose times omega plus s equal to c, and s is strictly positive and omega is unrestricted. Again, mu is greater than 0 to begin with as a barrier or penalty parameter. As we can see, both d mu and p mu has exactly the same KKT condition we're talking about in the previous slide. Okay, and the equation 3 we can rewrite as a xj times sj equal to mu, and this is the part. Okay, xj times sj, each one of them, since this is two diagonal multiplied together, and times a vector of 1, which is make it back to from a n by n matrix back to a n by 1 matrix in that case, and moving the mu to the right hand side, and that's what we got xj times sj equal to mu for all the j from 1 to n. So let x mu and omega mu and s mu are basically the current solution feasible solution for P mu and D mu and problem, and for each mu greater than 0. We can calculate the duality gap between P1 and D1 using the x mu and omega mu equal to C transpose times x of mu times minus B transpose times omega of mu. The mu here is, setting a penalty parameter, and we can get x. And this is basically the difference, we call the duality gap, is the difference between the primal objective function to the dual objective function. Since the primal is minimization, problem, and dual is a maximization problem in our development, so primal objective function always greater than the dual objective function value. And I can convert it into a dual constraint, actually, right here, and equal to C transpose times omega mu times A minus B, basically. We can actually equals to S, And what we have right here is x mu transpose times S mu equal to N times mu, So this is a fairly straightforward development calculation. So from here on, we can actually see that the duality gap from primal objective function to dual objective function is N times mu, and mu is that barrier parameters. So as mu close to converges to 0, we're going to set this up systematically, and the duality gap, g of mu is also going to approach to 0. The corresponding x mu and omega mu, which is primal and dual solution, converge to the optimal solution for P1 and D1 respectively. So this is fairly straightforward solution and development. Let's look at the next slide. The basic idea for this primal and dual affine scaling method is, first, initially we find a feasible solution, x naught equal to belongs to S, and omega naught and S naught belongs to dt. And the first step, we are trying to find a feasible improving direction dxk, d omega k, and dsk. Then we're going to find the optimal step size, beta k, trying to move towards those new direction. And we want to make sure the direction for the primal variable dxk, and direction for the dual variable d omega k, and the direction for the dual slack is dsk are all moving to a feasible direction, and also improves my objective function. This becomes a little bit complicated, so we trying to do was we first set up a few intermediate measurement to help us to gauge the process, help us to measure how well we converge. First is the phi ik equals to xik times sik. This is one of the, basically is duality gap divided by n, basically. And this is what we call the duality gap. Second is the average of the duality gap, basically is the summation of the phi ij, phi ik altogether divided by n. So we call the average duality gap. The next one is the minimum duality gap, which is we pick the minimum one, phi minima k. It is called minimum duality gap. Finally, the theta k is the gap ratio. It's the average duality gap divided by minimum duality gap. So these are the measurements we're trying to see if how the algorithm converge in that sense. In order to find a improving feasible direction for x, omega, and s, we're using a typical Newton's method, basically. Here, the Newton's method explained f of z is Rn to Rn mapping from z is n-dimensional, and fz is also n-dimensional. We're trying to find x also belongs to n such that f of x star equal to 0. Okay, and we're going to using a multi-variable Taylor series expansion and say z equal to zk, zk plus delta z. And if I move from current zk to a delta z, and we can approximate this by the original f of zk plus j times delta z. And J is actually the Jacobian matrix, for f of k, f of z. Okay, it is partial differential derivative for each one of the z function. If we let f of x star equal to 0 is equivalent to, say, f of zk plus delta z equal to 0, then the Jacobian zk times delta z approximately equal to the negative. Okay, move this to the right hand side. If I set this to 0 and move f of zk to the right hand side, and then we can calculate delta z as a d of z, which is our Newton's direction. So all I have to do is do an inverse function for the Jacobian matrix, and I can calculate delta z, and delta z is supposedly our direction. So we're using the same concept, okay, for developing direction for basically the delta x and delta omega and delta s in that sense. Okay, now let's take a look next slide. The Newton direction applied to the system we have 1, 2, 3, which is very this KKT condition right here, and we can come up with a one. Okay. Apply to the Newton direction for equation 1, 2, 3, the KKT condition, and we can give a point of xk, omega k, sk, the current solution, for some mu barrier parameter is positive, greater than 0. So, of course, currently xk is greater than 0, sk is greater than 0. The Newton direction can be applied to, okay, here's a times xk plus dxk equals to b. This is primal feasibility. A transpose times omega k plus d omega k plus sk plus dsk equal to c. That's a dual feasibility. And the final part is the complementary slackness. Okay, the capital XK represents the n by n matrix, and diagonal is the current xk. Sk represent an n by n matrix, is diagonal is the sk. Okay, here just that. So here we have these yellow dxk, d omega k, dsk, dsk, and dxk. So, and that's the right hand side. Some of those we can move to the right hand side of the equation. For example, a times xk can be moved to the right hand side. A transpose times omega k and sk can move to the right hand side. And although y portion can be moved to the right hand side. So capital xk times capital sk times the vector 1 can be also moved to the right hand side. That's resulting this system of linear equation. Okay. So here we say a times dxk, equals to b, negative b minus a times xk. Okay, so put a negative sign so it looks like this. So this is what primary feasibility, due feasibility, and complementary slackness condition. Okay, so we're trying to reorganize term, and the decision vectors we're trying to solve is dxk, d omega k, and dsk, which is the directions for primal and dual variables. Look at next one. It's a little bit complicated from the previous slide. We're trying to using a temporary variable to represent the right-hand side. We'll call it T, U, and V. Let's look at the next slide. The T is divided by B minus A times XK, and UK represent A transpose times omega K plus SK minus C, which is the, okay. And finally, the VK represent mu K times E minus XK times SK times E. So as we know, if XK is feasible to the primal constraint, then TK equals to 0. If omega and S belong to the T, then mu K terms equal to 0. Okay, as we have, okay, the following. Basically, A times dxk equal to tk, A transpose times d omega k plus dsk equal to mu k, and sk times dx plus xk times dsk equal to v. Okay. So multiply both sides by using equation 5, the middle one, and by A times capital XK minus times capital SK inverse equals to A times XK times SK inverse times A transpose times d omega k equals to, actually, A times XK times SK inverse times mu k, which is this part, minus this part, and A times xk times sk inverse times dsk. So just multiply both sides by this yellow part. And the equation 6, we know that also the dsk, which is the direction for the due slack, equals to, if I wanted to first move the sk times dxk to the right hand side and multiply both portion of the equation by sk inverse. Okay, so xk inverse times vk minus this part times sk inverse. So sk times dxk times sk inverse, and that part with a negative sign since we move this to the right hand side. And this gives us expanding the vk together, and that's what it is. Okay, so vk times x inverse, and this part will be sk times e. That's this part. And this part times mu times sk inverse times e, and that's this part. And finally, this part is directly from here. From here, sorry. Equation 6. So let's review. The TK actually represent the primal infeasibility. Okay, the current, if current X is not feasible, primary feasible. Second part, the UK represent the due infeasibility, if there exists. And finally, the VK represent the duality gap, hopefully in end of that, we're going to have it reach to 0. Okay, so that means the xk times sk equal to mu k in the future. Okay, so that's what we're trying to achieve. Again, also, let's look at the equation A. I'm going to multiply both sides of equation A by A times xk times sk inverse on both sides. And I can get A times capital XK times a capital SK inverse times mu k times xk inverse times E minus sk times E minus tk. Also, substituting the equation 9 into equation 7, and what we get, we can easily get this one. Okay, and then therefore we can calculate d omega k using this. So we just multiply this equation both sides by inverse of this, and that will get this. So I can calculate d omega k in the closed form, and everything we can pre-calculate it together, because this part is we can pre-calculate, this part we can pre-calculate, and so we don't need to repeat it doing this matrix multiplication. So these can be pre-calculated, and that the only computation burden will be in this inverse of this part. A times xk times sk inverse times h transpose, which is this side. And also, if xk is greater than 0 and sk is greater than 0, we're using d hat k squared equals to sk times sk inverse, which is this part. Okay, is positive definite because both x are positive and s are positive. I just xki divided by ski in that case. So we can easily calculate the direction of do slack equal to mu k, which is this part, minus a transpose times d omega. D omega can be calculated here. Also, the direction for the primal variable x can be calculated in this way. All right. So fairly straightforward. As after we have dsk, we can calculate dxk. However, if current primal solution xk is positive, is feasible to the primal feasible region, and omega k and sk satisfy the within T, which is dual feasible. And therefore, the tk and the mu k's are equal to 0. Let's take a look at the previous slide. So the tk portion and the mu k portion are 0. So only this part left. Okay. And d omega k can be easily calculated like this. And do slack, direction for do slack also can be easily calculated. And direction for the primal variable x can be also simplified. So if the current solution is primal and dual feasible, and the calculation of a direction is much easier. Why is that? And I want to discuss a little bit on this. The whole development so far represents actually this so-called primal and dual affine scaling method does not have to start with a feasible initial solution. So the only thing will be different is, if we look at here, if it's not primal feasible, then tk will not be 0. If it's not dual feasible, then mu k will not be 0. I can still calculate the direction for for dual variables. And also, if it's not feasible, I can still calculate the direction for dsk, the dual slack. All right. So it depends on the current solution, and it's feasible to the primal or dual problem. I just have these t, u, and v as a temporary variable during my calculation. So this is what we come up with, and I will show you later on using even Microsoft Excel. People can easily calculate, implement this primal and dual affine scaling method easily without even start with a feasible solution. Okay, and also we want to prove, okay, dxk transpose times dsk equal to 0. So the direction for primal variable and the direction for dual variable, dual slack, are actually perpendicular to each other. So therefore, we can calculate actually for each complementary slackness condition equals to mu k minus sik times sik, which is equal to mu k minus phi of ik. So this is our complementary slackness condition. Once this reaches to 0, then we have the optimal solution. Okay, so the first is if tk equals to 0 and mu k equals to uk equals to 0, then the current solution I already satisfied primal feasibility and dual feasibility. But once we reach so-called duality gap equal to 0, which is complementary slackness, so we basically update the mu k using the complementary slackness condition to update mu k and make sure it converges to 0 each iteration. And then after we obtain the Newton direction, we can calculate the new primal variable, new dual variable, and new dual slack by adding a step size of beta k. I'm going to stop this video because it's over 25 minutes. I want to start a new clip to talk about the step size calculation. Thank you.